Good afternoon, my name is Nicholas Gomez, and today we'll be describing what Navier-Stokes equation means and what it does. It is an equation that is able to analyze every fluid by three major properties, which are the gravity force per unit volume, the pressure force per unit volume, and the viscous force that it experiences per unit volume. If you add all of these three, you will be able to find the density times acceleration of any fluid and the way that it behaves. When using the Navier-Stokes equation, it is important to take three assumptions into consideration. First, that it's a Newtonian fluid, so the stress doesn't affect the shear thinning or thickening of the fluid. Second of all, that it's isothermal, so there's no major gains of heat or loss in the system. And lastly, it's incompressible. So that means that if it's less than 100 meters per second, according to the textbook, it does not have any major impacts on the way the velocity goes on a fluid. So now we will begin to derive the equation of Stokes' equation. As we know, the velocity is equal to three components I, J, and K, the different directions, and the respective velocity U, V, and W as a function of X, Y, Z, and T, which is time. As we know, acceleration is equal to the change in velocity over the change in time, and we have the same for the velocities of U, V, and W in I, J, K. First, acceleration is the change of velocity over the change of time, dV, dt, which is equal to the partial derivative of volume over time. And that is the local variable or local acceleration, which actually becomes zero if the flow is steady because it's non-dependent of time. And then we have our convective forces, which are the velocity times the of u times the partial derivative of v over partial derivative of x, and the same things for the y direction and z direction planes in v and w. These forces exist because flows don't travel in one dimensional way. They also may have some small components traveling in upwards, sideways, or straight through the tube. Now we can simplify this equation by having the local variable, which is the partial differential equation of dv over dt, plus the changes in the gradient, which correspond to ijk, change in d over dx, the change of d over dy, and change of d over dz, partial differential equations, times the velocity vector that's at the top of the equation. Now we can use these equations, also known as the total time derivatives, to add other variables such as pressure. And this way we will be able to get the first part of our Navier-Stokes equation. Next, it is useful to understand the differential equation of mass conservation, also known as the continuity relation, where you have the integral of the controlled volume and the differential equation of rho, which is the density over the change in time, times the change in volume, plus the change in rho I, A, and V going out, minus the change of rho A, V going into the system, or the inlet, is equal to 0. And this is kind of similar to Bernoulli's equation, where we would see the control volume of an object and then the mass flow rate going out and in of the system. We can also assume the integral of the control volume to be approximated to the partial derivative of density over the partial derivative of time times dx, dy, dz, because the change in density over time is very minute and can basically be ignored. We can, however, simplify this whole equation by making the flow incompressible, where the gradient of b is equal to 0. And in that way, we make the partial derivative of u, v, and w according to x, y, and z equal to 0 as well. It is time to move to the differential equation of linear momentum, where we basically take the same steps for an element volume derivation of Newton's law of a moving fluid, but apply it to the force. So now we know that the change of force is equal to the partial derivative over time of the control volume, of which we take the velocity times rho, which is the density, times the change in volume, plus the mass rate and velocity of the fluid, inlet going out, minus the flow rate and velocity going in, which again gets greatly reduced if we assume the element to be so small that it does not in fact change the density. Now it is good to review these equations because we understand that there's a relationship between the body forces and the net forces acting on the system. Now the only body forces that are due to the external fields would be gravity, magnetism, and electric potential. But again, the only one we'll consider will be the gravity force. And that's what we have. dF, gravity, is equal to rho g, which is the gravity, times the change in x, y, and z, dx, dy, and dz. Moving on to our forces, denoted by sigma ij, is equal to a matrix of negative p plus txx and the following viscous forces denoted as t, or tau. We see that we have hydrostatic pressure acting against our shear forces, which occur in every single phase if we treat every fluid particle as a cube. And this is what makes this cubic fluid particle a 9-component tensor. Here we show all the stresses acting in the x direction, not to make this picture clustered, and we see in one side we have the stress of xx times the change in dy dz, which is the area, thus giving us a force. And on the other side we have the exact same equation, but facing the opposite way, and we see we have the partial derivative of the stress in xx over dx times dx, which is showing us the distance that it travels from one side of the cube particle to the other. If we then assume that the change in the Fx force of the surface is equal to the change of the stresses in the x, y, and z direction in the similar manner that we saw all the stresses in x, we can arrive to the equation that the change in force over the change in volume is equal to the local force change in the pressure plus the x, y, and z directions according to their viscous stresses. By this definition, we can simplify the dF over dV viscous term, which is equal to the divergence of the viscous stress in the ij plane, where we have the 9-component phasor. Now we finally arrive to the fuel formula. Here we have the component that represents the change in gravity, which is the first one, minus the change in pressure gradients, plus the divergence of the viscous stresses is equal to the density of the fluid times the change in volume over the change in time. One good thing to note is that on the right side of the equation, we don't do m times the acceleration, which we're used to, but we do m over v, which is the volume, because we have to divide by it since we're considering each individual point in the Eulerian approach. A simplification we often use is calling the flow incompressible because it takes the shear stress away from the equation and makes tau ij equal to 0. Lastly, for Newtonian fluids, we'll have a viscous stress that's proportional to its elements in strain rates, as well as its own coefficient of viscosity. For incompressible flow, we'll have as followed. To conclude, this is the Navier-Stokes equation. It is a very important equation that helps us to determine all the properties of the fluid and how they behave. It can help us model the turbulence in an airplane, the way that a river flows, and even the weather pattern that it changes over a period that's longer than 1 week, which is what we're capable of right now. If we keep exploring and learning about this equation, our opportunities are endless. Now, I will test your understanding by asking a simple question. If you're traveling in a fighter jet with velocities u is equal to a times x squared minus y squared, and the velocity v is equal to minus 2axy, and w is equal to 0, due to a very cool loop that you do, A, determine under what condition is a solution to the Navier-Stokes moment equation, and B, determine the resulting pressure distribution when z is up, and if it meets the right conditions, of course. And I gave you a hint at the bottom so you can solve it better.